Let's look at FSRCNN, which was introduced in ECCB 2016, mentioned in here. Unlike the former slide SRCNN, FSRCNN processes the original low-resolution image directly without any kinds of upsampling, such as bicubic or bilinear, or some kinds of upsampling as a pre-processing step. Instead, it utilizes a learned deconvolution, or can be called as transposed convolution layer at the end to perform upsampling. This makes the proposed network, both faster and much more accurate than SRCNN, especially for real-time application. It consists of several key components such as feature extraction, shrinking, mapping, and nonlinear mapping, and expanding and deconvolution, which can be explained as the feature extraction can be explained with a 5 by 5 convolution on the LR image, and shrinking a 1 by 1 convolution reduce the number of feature maps and the channel number of feature maps, and nonlinear mapping can be described as that several 3 by 3 layers capture complex transformations, and expanding. Expanding is indicating that another 1 by 1 convolution increase the feature map channel size count. And deconvolution is indicating that 9 by 9 transposed convolution upsamples the feature spatial size to the high resolution output. Each convolutional layers, as shown in here, each convolutional layer is followed by a p-rel activation function for better learning dynamics. And this slide highlights one of the key components and FSRCNN's biggest strength, efficiency. Yeah. Yes, efficiency. First, to shrink the number of channels before the mapping layer, and then to expand the channel again before reconstruction. Not by direct, and shrink the number of channels and then expand it to the expected output feature maps. This can significantly reduce the number of parameters and the number of operations well. And this is all of the components of FSRCNN. And for example, we can look. For example, in here we can discuss another key design choice in FSRCNN, the replacement of wide filters with deeper stacks of small filters. As shown in here, two 3 by 3 convolution layer effectively cover the same receptive field as one 5 by 5 layer, but with fewer parameters such as 18 compared to 25. This can reduce the overfitting and improve some kinds of convergence. This principle of deep and narrow instead of shallow and wide became common in many later network architecture. It also allows the model to add more non-linearity and flexibility while keeping computation low. And a key difference between FSRCNN and traditional method is that FSRCNN learns the upsampling process itself. Instead of using kinds of fixed bicubic or bilinear or nearest neighbor interpolation, the model can include a transposed convolution, as shown in here, the convolution layer, which learns upsampling corners during the network training. for the network training, and this enables the model, the generator, as shown in here, the model to generate sharper and more natural-looking high-resolution images. And with this slide, we can discuss FSR CNN's training details. FSR CNN use the same L2 loss as shown in here. 아이고. L2 loss function as SRCNN, but it also introduced a two-step training approach. At first, the model is trained from scratch on the 91 image dataset. Then it is fine-tuned using the general 100 dataset to improve the generalization. The learning rate for the convolution and deconvolution layers are different as shown here, reflecting their different loads and sensitivities. This careful tuning helped the model, the FSR CNN model, converge faster and perform better across various datasets. And this slide also shows the different configuration of FSR CNN and compares their parameter size as shown here. The standard FSR CNN model has about 57,000 parameters. A smaller version, FSR CNN S, has as few as 4,600 parameters. In contrast, SRCNN models range from around 6,000 to 57,000 parameters depending on their configuration. Despite its smaller size, FSR CNN outperforms or comparably matches SR CNN in both speed and accuracy, proving that efficient design can be more important than structure of complex architecture. That's all thing of FSR CNN, and this is not any important for you guys. And let's talk about ESPCN. We introduced a new concept, the efficient sub-pixel convolutional network, which can be called as ESPCN, which were proposed by him. I don't know how to say his name or her name in CVPR 2016. Unlike the earlier method, ESPCN avoid upsampling the input. Instead of that, it processes the original low-resolution image and use a special sub-pixel convolution layer to directly produce the high-resolution output. This layer rearranges the feature maps into a higher resolution images, which can be explained with some kinds of slides, which can make the process both fast and effective. ESPCN proved to be nearly 10 times faster than SRCNN while achieving even better performance. And let's talk about ESPCN with conventional super resolution SRCNN and VDSR. In SRCNN and VDSR, the low resolution image is first upscaled as shown in here, interpolated, usually using maybe bicubic or bilinear interpolation, and then passed through some kinds of convolutional neural networks. And this only upsampling increased the input size and computational cost, especially when dealing with high-resolution images. In contrast, their proposed method, ESPCN, processed the low-resolution image directly without any kinds of upsampling. So the network then reconstruct the high resolution image using a sub-pixel convolution layer at the end. This leads to significantly lower computational complexity and faster inference time. And this slide illustrates how sub-pixel convolution layer work. The key idea of this layer is to rearrange multiple low-resolution feature maps into a single high-resolution output. For example, if the upsampling factor is 2 times, then 4 LR feature maps are combined into one HR image using a process called pixel shuffle. This rearrangement allows the network to operate in the low resolution domain, saving memory and computation, and then efficiently upscale the result at the final stage. This method is highly efficient and is particularly beneficial for real-time applications such as mobile or embedded device. And also, in this slide is also illustration of pixel shuffle layer, sub-pixel convolution. We can see an example of how sub-pixel rearrangement transform the LR feature maps into a HR image. Each colored cell represents a different channel in the feature map. These kinds of cells are reorganized spatially to form high-resolution output. Instead of treating each feature map as a separate image, the ESPCN treats them as building blocks for constructing a larger image. This novel idea achieves super resolution with significantly lower operation than traditional deconvolution, as shown in here. This slide compares SRCNN from 2014 and 2015 with ESPCN. ESPCN outperforms both versions of SRCNN and ANR, some kinds of papers and Apple and any other previous works. This performance boost comes from the fact that ESPCN avoid upsampling early and use the sub-pixel convolution layer, which can be called as pixel shuffle layer for efficient reconstruction. It marks an important step in the evolution of lightweight and fast SR models. And now we will talk about SR again, which was introduced by, I don't know how can I call his or her name, in 2017 in CVPR. SR again was the first model to apply generative adversarial network to the super resolution task. Unlike earlier method that focused solely on maximizing PSNR or SSIM, SR again aimed to improve perceptual quality, how realistic the output looks to the human eye. And it also introduced a new loss function that combines adversarial loss which can be called as just GAN loss, with a perceptual loss based on VGG features, moving away from traditional L1 and L2 losses. And this slide simply illustrate the structure of GAN used in SRGAN. The generator takes in a low resolution image and produce HR images. 깨졌네. HR image, HR reconstructed output images. And discriminator tries to distinguish between the generated images, HR images, and real high-resolution images. For the network training, generator and discriminator, the generator is increased to fool the discriminator, while the discriminator improves its ability to tell the difference between reconstructed HR images and original HR images. This adversarial training process or manner push the generator to produce much more realistic texture and finer details beyond what MSC-based previous works can achieve. And the generator loss in SRGAN is a combination of several components, but this is not any important for you guys, and this one is what I want to talk about. MSC loss is indicating that how measure pixel-wise accuracy, and adversarial loss is that increasing photorealism or realism by pushing the generator to produce outputs that resemble the corresponding HR real images. And vision loss, which can be called as perceptual loss, which is indicating that measures semantic similarity in feature space using a pre-trained vision network. Together, these kinds of loss help the generator, the network, learn not just to reconstruct pixels, but to reproduce high-level structures or high-level semantic information or some kind of texture that makes images appear sharper and much more natural. And this slide, we can see the mathematical formulation of the visual loss. The loss is computed as the Euclidean distance between visual feature, as shown in here, visual feature maps of the generated images, and the ground truth images. Multiple layers of visual can be utilized to capture different level of visual features from low-level edges to high-level semantic structure or context. This kinds of loss allows the model to focus on the overall look or feel of the image or feel of the data rather than just exact pixel values. It's a great example of using pre-trained network to guide the training of generative models. And this slide outlines the training procedure for SRGAN, but this is, I think, not any important for you guys. And we compare different loss functions and their impact on super resolution performance. As shown in here, we utilize some kinds of adversarial loss or GAN loss. And what I want to talk about is what is MOS, mean opinion score. This is the training details, and what I want to talk about is just this one. Mean opinion score, which measures which measures perceived image quality based on human evaluation. It's often more aligned with visual quality than not just PSNR, not just PSNR and SSIM. We can see that SRGAN, 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 which use a combination of L2 adversarial loss, GAN loss, and residual loss, achieve significantly higher MOS score than model trained with just L2 loss. This confirms that perceptual loss function leads to images that look better to the human eye, even if PSNL and MSC and some kinds of evaluation metrics value is slightly lower than previous one, and just similar to the HR target image MOS score. And this slide visually compares output generating using different loss function, and model trained with only L2 loss tend to produce such a blurry output and low contrast images. On the other hand, model which was trained with perceptual loss and adversarial loss, GAN loss, generate much more sharper and more realistic texture and edges. This can highlight the crucial point, which is that maximizing PSNR does not always mean better image quality. Sometimes allowing the network to generate much more realistic details or textures, even if they deviate slightly from the ground truth, gives much more pleasing results, visually pleasing results. And this is also same things. The author summarized two proposed models, SR-LesNet and SRGAN. SR-LesNet designed to maximize some kinds of evaluation metric value, PSNR, MI, SSIM, much better than SRGAN, but depending on SRGAN optimized for perceptual quality by using adversarial loss and rigid perceptual loss. Depending on the application, one might prefer SR-LesNet for quantitative accuracy or SRGAN for perceptual or visual realism. This dual approach provides flexibility for different tasks, whether scientific imaging, media enhancement, or consumer applications. And this is not any important for you guys. And let's talk about EDSR and MDSR, presented by Lim, which was presented at CVPR Workshop 2017. EDSR stands for Enhanced Deep Super Resolution Network. And this slide just shows the architecture of EDSR. It consists of 32 LED blocks, and each convolutional layer has 256 channels. There are 67 convolutional layers and 43 million parameters, such a lot of parameters, and batch normalization, as shown in here. Batch normalization is removed from the residual blocks to improve performance, SR performance, and residual scaling is used to stabilize training when the model size becomes larger than before. Despite its depth and complexity, EDSR is highly effective at recovering or reconstructing fine texture and details. Here we can see the training configuration of EDSR. EDSR? Just EDSR, not MDSR. We just talk about EDSR. Training is performed using L1 loss instead of L2 loss. And the model is optimized using Adam Optimizer with beta 1 set to 0.9 and beta 2 is set to 0.999. The learning lag is halved every 200k mini batches, and a mini batch contains 16 training patches. So that's the training details, and EDSR use geometric self in ensemble for the network testing to further enhance accuracy by averaging prediction from flipped and rotated input images. 그러니까 로테이트해서 이런 영상이 있을 때, 이런 영상이 있을 때 이렇게 해서 SR을 진행을 하고요. 그럼 결과 나오겠지. 이렇게 해서도 SR을 진행해. 그리고 이걸 다시 돌려. 이거는 원본이겠죠. 요놈들끼리의 평균을 내. 그러면 다른 영상이 들어가서 테스트를 해서 요놈들의 평균을 내니까 조금 더 에버리징 효과가 있겠죠. And this slide illustrates geometric self-ensemble testing. For the network inference, for the test inference, the low resolution input is flipped or rotated in 8 different ways. The model generates a super reserved image for each transformation, and then all outputs are inverse transformed and averaged to produce the final SR result images. This ensemble technique does not require any kinds of additional training, but boosts performance by leveraging image symmetry or redundancy. It's a novel and fancy way to squeeze more accuracy from a single model at the test time. And this slide shows the effectiveness of their proposed method, much better than before. And we will briefly talk about DBPN, which stands for Deep Back Projection Network, which was introduced by maybe Harris in CVPR 2018. This model takes inspiration from a classic image restoration technique called maybe iterative back projection. The key idea is to refine the HR output by continuously comparing it with the original error input through repeated up and down sampling stages. By implementing the principle in a deep neural network, DBPN, DBPN is able to iteratively correct errors and reconstruct fine image details for effectively than one-shot SR models. This slide simply compares 4 different architecture strategies for SR, super resolution. The first one, predefined upsampling, is just we used in only model like SR-CNN or VDSR, which start with bicubic or bilinear upsampling. And the second one, single upsampling, is just as shown in FSR-CNN, where upsampling is performed at the end. And the third one, progressive upsampling is just gradually increase resolution using multiple stages. Like maybe we did not cover some kinds of this paper. It just two times, two times, two times, which is meaning that just 8 times SR. And the last one, iterative up and down sampling strategy is used in this paper, DBPN, allowing multiple refinements through feedback. Among these kinds of upsampling strategy, DBPN's feedback mechanism provides richer feature learning and often yield superior results in challenging scenarios. In here, we can look at the core components of DBPN, just up, down projection process. Each up projection unit maps the error features to HR features. Error features to HR space, while the down projection unit maps it back. These kinds of projections are not just a forward pass, they include error correction steps that can help the network learn to reconstruct details or context which were missed in earlier stage. As shown here, just to make the network memorize some kinds of errors. And what makes DBPN special is iterative refinement. Each projection unit not only generates new features but also learns from the previous stage, as shown here and here. Learns from previous stage to improve the reconstruction accuracy or performance over time. And this slide shows the details, the projection process, as shown in here. A projection unit generates an intermediate HR map, and the down projection unit maps it back to the error space. The difference or residual the difference or residual between the input error and reconstructed error, typo error, is projected again to HR, which is helping recover or reconstruct the missed details. This feedback loop is repeated across the stages, which is allowing the network to revisit earlier errors and refine its output. This is conceptually different from feed-forward model, just feed-forward model, which generate the result in one pass. That's the most important difference between the former works, the previous works. And DBPN comes in several variants: DBPN S, M, L. DBPN S is shallow, and DBPN M maybe medium, maybe, and DBPN L is indicating large. A deeper variant called DDBPN, dense DBPN, as dense connection between projection units and utilize RGB inputs directly instead of some kinds of grayscale images, as shown here. And this version achieves even better results on standard benchmark. And this slide compares DBPN's performance with other networks like VDSR, DRCN, and LabSRN and SRCNN. and some kinds of papers on set5 dataset, maybe on set5 dataset for 4 times SR and 8 times SR. The key component, the key aspect is that deeper back projection model like DBPN-L outperforms traditional feed-forward models in both PSNR and some kinds of visual quality. And the iterative structure not only allows deeper understanding of the image, but also provides a maybe can I say this as can I say with this word built-in correction mechanism, which help in reconstructing finer texture. And this slide also the quantitative comparison to the previous works, but not any important for you guys. And this one is also not important for you guys. And we will briefly talk about residual dense network for image super resolution, which can be called as RDN. RDN, which was proposed in CVPR 2018. RDN introduced the concept of residual dense block, RDB, which combined the benefits of residual learning and dense connectivity. It fully exploits hierarchical features by fusing output from multiple convolution layers at both global and local levels. This allows this RDN model to learn rich multi-level representations for each image patch, which leads to highly detailed and natural-looking SR results. This slide shows the architecture of RDN and RDB. It begins with shallow feature extraction, maybe a shallow feature extraction, and then some kinds of residual dense block. And each RDB extracts local feature, as shown here, local features and some kinds of global features. We can fuse the feature using one-by-one convolution for local feature fusion, and we can add some kinds of residual connection for stable learning. Residual connection, as shown here, residual connection. And at the end, the global feature fusion combines the output, global, as shown in here, global residual learning and global local residual learning. Global feature fusion combines the outputs from all RDB and pass them to the upsampling module, as shown here. This structure captures both fine and broad image details, which is making RDN one of the most powerful SR models to date. And each RDB is composed of 넘어가자. Okay. And each RDB, as shown in this slide, each RDB is composed of dense connected layer and local feature fusion and local residual learning. Dense connection is that where each layer receives input from all previous layers in the block, and local feature fusion, which can be called as LFF, is indicating that implemented via a one-by-one convolution to combine all dense outputs. And the third one, local residual learning, is indicating that as just adding the fused feature back to the input of the block. This structure allows the RDN to extract highly detailed local features and can ensure a smooth flow of information even in such a very deep network. And one of the RDN key innovation or key contribution is the contiguous memory mechanism. In this structure, the state of the previous RDB is passed not just to the next block, but to every layer within this one. This maintains a continuous flow of information throughout the network and help preserve important features across the depths. As a result, RDN can train much deeper architecture while maintaining stable gradients and enhancing representation power. It's a perfect example of how dense connectivity and residual learning can complement each other. And this slide just illustrates on local feature fusion, LFF. After collecting dense features within RDB, the feature map size become large due to the concatenation, as shown in here. To manage these kinds of issue, one by one convolution compress the channel of feature, reducing the number of channels. And these operations is control the memory size. Control the memory size and prevent overfitting and ensure that only the most relevant local features are passed on. That's it. LFF acts like a filter that can keep important or essential information while discarding redundancy or contributing to the overall efficiency and power of RDN. And RDN also incorporates local residual learning in each RDB. This one. While dense connection ensure that features are richly reused, local residual learning, LRL, further improve the training dynamics by allowing each block to learn a residual instead of full transformation. And this can have two benefits. The first one is stabilize gradient flow in deep network, and it let the SR network or some kind of generator focus on learning only the difference needed for SR, which accelerates convergence and improve the SR performance or accuracy. RDN combines these kinds of technique, as mentioned earlier, these kinds of techniques to become both deep and trainable. And after extracting the essential features from all of RDB, RDN applies Global Feature Fusion, GFF, and Global Residual Learning, GRL, which can be called as GRL. 안 써놨네. 다음 장에 있나? 여기 있네, GRL. GFF combines multiple level features, as shown in here, here. Global multi-level features from each RDB using 1x1 convolution and 3x3 convolution. And GRL as the fused global features to the shallow feature extracted at the very beginning. And this final fused representation contains rich hierarchical information across the entire image and can be used as input to the upsampling module, which is resulting in highly detailed, high-resolution reconstruction. So that's it. To summarize, we can explain some kinds of training details. We utilize DIV2K dataset with 800 training and 100 validation images. And degradation model is including bicubic interpolation and blur downsampling using a Gaussian corner of size 7x7. And images are maybe augmented by flipping horizontally or vertically and rotating 90 degree. And patch size was 16 and patch size is 32x32. Training is processed using Adam Optimizer and with the learning rates at 어딨지? learning rate? 0.0001 and halved every 200 epochs. And this training setup allows the proposed RDN to generalize well and to various degradation types. And this is not any important for you guys because they always say in their result section, our method is outperforming the previous works. So this is not any important for you guys. And we just briefly and simply check the quality of their proposed method. At first, their PSNR and SSIM achieved the state-of-the-art performance, and in this sample is also they achieved state-of-the-art SOTA performance. And compared to traditional models, RDN produced outputs with much better texture recovery, mentioning here, texture, and sharper contour, fewer artifacts, and that's it. These kinds of results show that RDN's architecture complexity directly translates into meaningful improvement in image quality that are visible to human eye, maybe with here, but I cannot agree with this kind of suggestion and their results section. And this paper is also important for SR task. And this paper is included in recommendation list. So SR lecture is over here, and I will upload this video lecture on the LMS right now. And thank you for listening this